Good evening. My name is Mian Pan, and I am a graduate student in the Master of Science in Data Science program of the School of Applied Computational Sciences and the Meharry Medical College. Today, I will present my capstone project, which focuses on predicting unmet healthcare needs among children with autism spectrum disorder, or ASD, using interpretable machine learning. About about 1 in 31 US children has ASD. This means many children and families rely on timely and consistent access to healthcare. Yet, not every child receives the care they need. So, my project asks a simple but important question. Can we identify which children are most at risk of unmet healthcare needs early enough to intervene? To answer that question, I developed an interpretable machine learning framework that predicts risk and helps reveal the factors behind these disparities. Here is a quick roadmap of my presentation. I will begin with the problem and why it matters, then introduce the data and the exploratory analysis. Next, I will walk through the methodology and the model selection, followed by the main results, explainability, and the fairness findings. I will close with the future directions and the key takeaways from this project. Children with ASD often need ongoing medical behavior and specialty care because those needs are often continuous and coordinated. Delays in access can have serious consequences. In practice, families may face barriers such as cost, insurance limitations, referral difficulty, or limited access to specialized services. These barriers can leave important healthcare needs unmet and may worsen disparities in care. That is why this problem matters. It is not only about predicting risk, but about identifying which children may need support sooner. My project addresses this by building an interpretable machine learning framework that can help flag higher risk children while also showing which clinical and social factors are most strongly associated with unmet healthcare needs. This project used the data from the 2022 National Survey of Children's Health, a nationally representative US survey. The original dataset included 54,103 children, and from that, I identified a cohort of 1,788 children with current ASD. After pre-processing, the final analytic dataset included 28 predictors covering demographic, clinical, social-economic, and environmental factors. For example, poverty ratio was used to create a more interpretable poverty level variable and then removed. And the FIPSST was reserved only for state-level visualization. The target variable in this study was a binary outcome called unmet need. It indicates whether a child experienced an important healthcare access problem, such as unmet care, difficulty seeing a specialty, or difficulty obtaining a referral. A key early finding from exploratory analysis was that this was an imbalanced classification problem. In other words, children with unmet healthcare needs were the minority class, not mattered because overall accuracy alone could be misleading. So from the beginning, the modeling strategy focused more on recall and threshold selection in order to better identify children at risk. This slide shows the overall methodology used to build the predictive framework. SH 2022, I first selected the ASD cohort. I then carried out pre-processing and feature engineering, including handling missing values, encoding variables, constructing clinical comorbidity indicators, and creating more interpretable features such as poverty level. Next, I split the data into training, validation, and test sets using a 60, 20, and 20% structure. This allowed the model development, threshold tuning, and the final evaluation to remain separated. I then trained and compared the 4 classification models: logistic regression, random forest, support vector machine, and XGBoost. Because the outcome was imbalanced and the goal was to avoid missing at-risk children, I focused primarily on recall with F1 score as a secondary measure. Using the validation set, I tuned the classification threshold to improve the balance between identifying positive cases and limiting false positives. The final model and the threshold were then evaluated on the independent test set. Finally, I extended the evaluation beyond the predictive performance by including interpretability, fairness analysis, and state-level geographic visualization. Overall, this pipeline was designed not only to predict unmet healthcare need, but to do so in a way that was transparent, reproducible, and practically meaningful. This slide presents the core modeling results. I compared the 4 supervised learning models: logistic regression, random forest, XGBoost, and the support vector machine, because this was a healthcare prediction task with an imbalanced outcome. I focused primarily on recall with F1 score and other metrics used to assess overall balance. Among the models tested, logistic regression performed the best for the purpose of this project. At the selected threshold of 0.30, it achieved a recall of 0.883, meaning it identified most children who had unmet healthcare needs. It also showed the best balance between recall, F1 score, and interpretability. The threshold plot shows why threshold tuning mattered. Lower thresholds increase sensitivity, while higher thresholds reduce it. I selected 0.30 because it gave strong recall while keeping precision at a reasonable level. So the main takeaway from this slide is that logistic regression was not just statistically competitive, but also the most practical and interpretable choice for identifying at-risk children earlier. After selecting the final model, I used the explainability methods to better understand what was driving its predictions. The shape analysis showed that the most important predictors included anxiety, overall health, age, insurance type, ADHD, depression, school safety, and family structure. These results suggest that unmet healthcare needs are shaped by both clinical complexity and social context. In other words, the model was not simply detecting one narrow medical factor. Instead, it reflected a broader pattern in which children with more health challenges and families facing greater access barriers were at higher risk of unmet need. The value of explainability here is that it makes the model more transparent and more useful. It helps to translate a prediction into insight by showing which factors are most strongly associated with risk. So the main takeaway from this slide is that the final model not only identified at-risk children, but also highlighted actionable clinical and social drivers that may help guide targeted support. Because this project applies machine learning in a healthcare context, I also evaluated fairness and considered how the model should be used responsibly. The fairness analysis showed that recall was relatively consistent across demographic groups, which suggests that the model was fairly similar in its ability to identify children with unmet healthcare needs. However, false positive rates were less balanced, especially across racial and Hispanic subgroups. This matters because it means the model may overpredict risk for some populations, even while doing a reasonable job of identifying positive cases overall. From an ethics perspective, this means the model should be used as a decision support tool rather than a standalone decision maker. It may help flag children who need closer attention, but it should not replace clinical judgment or policy context. It is also important to acknowledge limitations. These results are based on cross-sectional survey data. Some subgroup sizes are small, and the data may reflect broader structural inequities that the model can learn from. So the main takeaway is that predictive performance alone is not enough. In healthcare, responsible use requires transparency, fairness evaluation, and cautious interpretation. This slide focuses on what the results really mean beyond the model performance. One of the clearest findings from this project is that unmet healthcare needs among children with ASD are shaped by both clinical complexity and the social context. The model highlighted a broader pattern involving mental and behavioral health conditions, overall health, insurance-related factors, and family or environmental conditions. This matters because it suggests that unmet healthcare needs is not simply an individual, a clinical issue. It reflects a combination of health burden and access barriers. A strength of this project is that the framework was not only predictive, but also interpretable. It combined the model comparison, threshold tuning, explainability, fairness analysis, and geographic visualization to provide a more complete picture. At the same time, there are important limitations. The data are cross-sectional and self-reported, so the results show associations rather than causation. In addition, some subgroup sizes were small, which makes the fairness estimates less stable. So overall, the key insight is that interpretable machine learning can help identify children at risk earlier, but it should be used carefully and in the context of a broader healthcare and equity considerations. The slide highlights several practical recommendations and future directions for extending this work. First, this framework would be used as a decision support tool to help identify children with ASD who may be at higher risk of unmet healthcare needs. In practice, that could support earlier outreach, more targeted innovation, and better informed resource allocation. However, it should support decision-making, not replace clinical judgment. Second, the framework could be strengthened by expanding the data. For example, integrating multiple years of NSCH data would improve robustness and help address the small sample sizes that affected some subgroup fairness estimates. Finally, future work could explore fairness-aware modeling approaches, incorporate geographic information directly into prediction, and evaluate additional models while maintaining interpretability. Overall, the next step is not just improving model performance, but improving usefulness, fairness, and real-world relevance. To conclude, there are three main takeaways from this project. First, interpretable machine learning can help identify children with ASD who are at risk of unmet health care needs. Second, this risk is shaped by both clinical complexity and social barriers, not by medical factors alone. Third, in a healthcare setting, prediction is only part of the goal. Responsible use also requires interpretability, fairness, awareness, and careful context. Overall, this work shows that data science can do more than predict risk. It can help reveal where support is needed most. This work was also presented as a poster at the Meharry Southeast Hub Annual Symposium 2026, which was a meaningful opportunity for me to share the project and learn from others. I would also like to sincerely acknowledge my advisor, Dr. Sao, my program, and all those who supported me during this capstone journey. Thank you very much for your time and attention, and I welcome your questions. Thank you.
Great work, great presentation, Mian.
Thank you.
And I'm
So
happy
much.
to see you grow like this. Really, really, thank you.
Thank you.
You guys are make me win. Really, I'm feeling like this. Not all the projects are mentored by me, but I know from you the beginning, right? So when I see that you're presenting in such a beautiful way and confidently, really, I'm feeling very, very happy. I have no words to say. So yes, the floor is open for questions. Yes.
Hey man, I'm sorry if it's so loud, but what inspired you to do this
That's a
subject?
really good question. I anticipate your question, this question, because first of all, I have a dear friend. She unfortunately has a very severe autism children. I witnessed all her struggle through these years. Her son just a half a year older than my daughter. Well, no, my son. So that's also I witnessed other families with autism children. I witnessed all the struggles they experience all those years. So I just when I look at the data Dr. Sao gave me, I found I see lots of autism children through this data. So I decided to do something um, with this group of children with autism. That's a really good question. That's my inspiration for this project, basically.
So any other question to her? Otherwise, we'll move to lectures.